In the realm of data science and machine learning, defining the primary metric is a crucial step. This metric serves as the guiding star for evaluating the performance of your models. It helps in determining how well your model is performing and whether it meets the business objectives. Without a well defined primary metric, it becomes challenging to assess the effectiveness of your model, leading to potential misinterpretations and misguided decisions. Primary metrics are essential because they provide a quantifiable measure of success. They align the model's performance with business goals, ensuring that the model delivers value. For instance, in a customer churn prediction model, the primary metric could be the accuracy or the F1 score, which directly impacts business decisions. By focusing on a specific metric, data scientists can fine-tune their models to optimize for what truly matters. There are various types of primary metrics, each suited for different types of problems. Common metrics include accuracy, precision, recall, F1 score, ROC AUC for classification problems, and mean squared error, MSE, mean absolute error, MAE, and R squared for regression problems. The choice of metric depends on the nature of the problem and the business objectives. For example, in a medical diagnosis model, precision might be more critical than accuracy to minimize false positives. Selecting the appropriate primary metric involves understanding the problem domain and the business goals. For instance, in a fraud detection system, recall might be prioritized to catch as many fraudulent transactions as possible, even if it means having more false positives. Conversely, in a recommendation system, precision might be more important to ensure that users receive relevant suggestions. The key is to align the metric with the specific needs and constraints of the project. In some cases, a single metric may not be sufficient to capture the performance of a model comprehensively. Balancing multiple metrics can provide a more holistic view. For example, in a classification problem, both precision and recall are important, and the F1 score, which is the harmonic mean of precision and recall, can be used as a balanced metric. Understanding the trade-offs between different metrics is crucial for making informed decisions. Consider an e-commerce platform aiming to improve its recommendation system. The primary metric chosen is precision, as the goal is to ensure that users receive highly relevant product suggestions. By focusing on precision, the data science team can fine-tune the model to minimize irrelevant recommendations, thereby enhancing user satisfaction and increasing sales. This case study illustrates how aligning the primary metric with business objectives can drive tangible results. In a healthcare diagnosis model, the primary metric might be recall, especially if the goal is to identify as many cases of a disease as possible. High recall ensures that most positive cases are detected, which is crucial in medical settings. However, this might come at the cost of lower precision. By understanding this trade-off, healthcare providers can make informed decisions about the model's deployment, balancing the need for comprehensive detection with the risk of false positives. Once the primary metric is defined, it is used to evaluate the model's performance during training and testing. This involves splitting the data into training and test sets, training the model on the training set, and then evaluating it on the test set using the primary metric. This process helps in understanding how well the model generalizes to unseen data and whether it meets the desired performance criteria. Defining the primary metric is not a one-time task. As the model is iteratively improved, the primary metric serves as a constant benchmark. Data scientists experiment with different algorithms, feature engineering techniques, and hyperparameter tuning to optimize the model. Each iteration is evaluated against the primary metric to ensure that the changes lead to tangible improvements in performance. Defining the primary metric can be challenging due to various factors such as data quality, imbalanced datasets, and evolving business goals. For instance, in an imbalanced dataset, accuracy might not be a reliable metric, and metrics like precision, recall, or the F1 score might be more appropriate. Additionally, as business objectives evolve, the primary metric might need to be redefined to align with new goals. Flexibility and adaptability are key in this process. Several tools and libraries can assist in evaluating primary metrics. Popular libraries like scikit-learn, TensorFlow, and PyTorch offer built-in functions to calculate various metrics. These tools provide a standardized way to measure and compare model performance, making it easier for data scientists to focus on model improvement. Visualization tools like Matplotlib and Seaborn can also help in understanding metric trends and making data-driven decisions. In conclusion, defining the primary metric is a foundational step in the data science and machine learning process. It ensures that the model's performance is aligned with business objectives and provides a clear benchmark for evaluation. By carefully selecting and balancing metrics, data scientists can build models that deliver real value. Continuous evaluation and adaptation of the primary metric are essential to keep pace with changing business needs and to ensure sustained model performance. As the field of data science evolves, new metrics and evaluation techniques are emerging. For instance, fairness and bias metrics are becoming increasingly important to ensure that models are not only accurate, but also equitable. Additionally, explainability metrics are gaining traction, helping stakeholders understand how models make decisions. Staying abreast of these trends is crucial for data scientists to build robust, ethical, and transparent models that meet the complex demands of modern applications.